All right. Well, I'm going to have to start the class.
Yes, that's what I was trying to say. He still thinks you're old.
So I'm moving your seat a little bit closer because we have another student who find it a little bit. So we'll try to minimize the crosstalk. Yeah. All right. What I really need is a remote keyboard so I can, actually stay on that side and be able to type and, work, operate the computer on that side. Yes, I know they have a, special software that let my cell phone control the computer, but I don't think that's a very effective way of typing. For some of you, maybe you can type on the cell phone. I cannot.
Connect.
Connect?
Microsoft Connect.
Microsoft Connect? This is Linux. We just use VNC. All right. So did anyone went ahead of me and tried to solve this problem to prove that this statement here is saying the same thing as this statement here? Nobody? You guys are all waiting for me to do it? Okay, we'll go ahead and do it. Okay. So what we'll do is we'll pick one, okay, just pick this one in this case, and then we'll work it out. Okay. So the question is, let me change the layout a little bit so that people in the back can see it, because I know sometimes it's hard to see the bottom part of the screen because of the rows of students ahead, in front of you. Is that okay so far? I mean, can everybody read the bottom row of the text editor? Is that okay? All right. Okay, so what we have here is, okay, this part here is just using the and, and that's it has the same rules as multiplication. In other words, I can remove the parentheses or change the arrangement of parentheses, and it will still mean exactly the same thing. Okay? In other words, what I'm saying is A and B and C would mean exactly the same thing as A and B, and then the whole thing and C. Is that okay? Now, how do we call this rule in algebra?
Associative.
Associative. Exactly. It's called the associative property of an operator. It applies to multiplication and addition in arithmetic, but it also applies to conjunction and disjunction in Boolean algebra. All right. So that means, with this, I can rearrange this statement just a little bit so that we have the other end on the outside, and then this end, the first end in the inside, right next to the disjunction, and then the other end is on the outside of the disjunction. Is everybody doing okay with this transformation? I'm just applying the associative law of Boolean algebra, which works exactly the same way as the associative law for multiplication and addition. Is that okay?
Yep.
Okay, next we'll use the distributive law because we want to break apart the disjunction. So in this case, we'll end up with something or something, and then the entire thing will have this part at the end. What is in the middle part here would be z equals x, and z is greater than or equal to x, because I'm combining the first part of the or with the common part of the and. And then the second part would be combining z equals y and then the component outside of that. Are we still doing okay? I'm applying the distributive law, which is, if you just look at this or as an addition and this and here as multiplication, you already know how to do it in regular algebra. And it works the same way in Boolean algebra. Are we doing okay?
Great.
I can simplify this a little bit already because if I don't simplify it, it will be a little bit too long and too lengthy. So I'll go ahead and simplify this a little bit here. You don't have to copy this, on a piece of paper unless you think it will help to reinforce the idea. But I just want you to kind of focus on the concepts because I won't ask you to prove something like this, with your homework assignment or the test. What do you think I can simplify oops, here. If you just look at this highlighted part here, is there a better way to say that z equals x and z is greater than or equal to x?
Just z is greater than.
Yeah. Okay, this is a conjunction. How many people know what is, do you remember something like this? In your math class, it is set theory. Intersections versus the union. No, not really.
Usually English.
Sorry?
Usually that's for English. I use that for English stuff. But
For
not
English
diagram.
stuff?
Yeah.
Okay.
Can you use a darker one? I couldn't see it.
Okay, we can also look at this in another way. When you say something and something, are you making the statement more restrictive or are you making it more general? It's more restrictive because you need both sides of a conjunction to be true for the entire thing to be true. So if you look at this highlighted part here, z equals x has to be true, z is greater than or equal to x has to be true. If I tell you that one can be tossed away without changing the meaning of the conjunction, which one do you think you can toss away without changing the meaning of the conjunction? Z is greater than or equal to x. Because it is more general. Okay? It overlaps completely with the other one, but yet it is more general, and we can toss that away. So that means this part here is condensed into just z equals x. Okay?
Isn't it the reverse? You can just lose a whole lot of meaning by getting rid of all the derivatives and equal to.
And that's true.
Wouldn't you just get rid of z equal to x? Now x can only be one value, whereas before x could be an infinite number of values.
Well, it will end up as z equals x or z equals y without stating any relationship between x and y. Well, we'll go ahead and, okay, that means the original statement may have something wrong with it. But it doesn't have anything wrong, I don't think. Well, it is going to simplify to just z equals x or z equals y, but it doesn't say which one is larger. Well, let's go ahead and just go through this and find out what it's going to do. Okay, we have another or here, and we have an and here, so we can reapply the distributive law. So we'll go ahead and do that part.
Distributed, you would z is equal to x and z is greater than or equal to x, or z is equal to y and z is greater than or equal to x, not z is greater than or equal to y. That's where you make your mistake.
Okay.
Because you're distributing the same value for both sides, and you distributed a different value for both sides, which makes it wrong.
Okay, that makes sense. Okay, let me backtrack. I think I made a mistake here. Okay, I was trying to distribute this term. I was trying to distribute this term over these two, and I made a mistake here. That's not supposed to be z is greater than or equal to y. It's z is greater than or equal to x. Did you guys see where the mistake was? Good. That's good observation. Well, that changed everything. Because the first part will still be simplified. Okay, we can still simplify this whole thing to just z equals to x, But the second part, doesn't get simplified at all because there's no way to simplify this. But we can rewrite it in a certain way. What is the other way to rewrite z equals y and z is greater than or equal to x? We know that z and y are interchangeable in that conjunction because they are the same. So now we can. Yep, that's it. So in here, we still have to keep this part, which is z equals y, but at the same time, we can now say y is greater than or equal to x. And then the whole thing still has z is greater than or equal to y on the outside. Are we still doing okay so far? And we have to keep in mind how we want it to look like, which is something like this. I'm not sure we are heading that way. Okay, let's do the simplification here. I think we will end up with the same thing that we began with. So once again, we have a disjunction in the middle, and we want to distribute these two terms over this term here. So we'll have z equals. So we'll end up with something or something. This will be z equals x, and z is greater than or equal to y, or the other one, which is this entire term, and z is greater than or equal to y, and I don't think we are getting any closer because we end up with the same thing. So we have z equals x, and x is greater than or equal to y. Is that okay? Because we have z equals to x, so we can use z and x interchangeably. And then on the other side, we have z equals y, and the same thing, y is greater than or equal to x. Because these two actually mean the same thing when z and y are the same. So we did not go anywhere, did we? Well, we did go somewhere, but not to the point where it is equivalent to this. Well, we can also work on this one here. We're actually closer now. So we'll go ahead and change this one instead. Okay. Let's see if I can this part here. Okay, we want to make this look like this one here. And I can see the only difference is one has a greater than instead of a greater than or equal to, and that's when z equals y. In other words, we want to see if we can get rid of this equal here and still retain the same meaning of the entire thing. Okay? And how do you think we can do that? I have an answer already. I'm just checking with you guys. Now, I'm not going to finish this because it will look really messy. The way it's looking is already kind of messy. Okay. The way we can do this is, okay, I'll just repeat the first part, which doesn't need any extra work. But the second part here, instead of stating it as a single comparison, I can state this as y is greater than x or y equals x. Is that okay? Okay. Can everybody see that this is really just the same thing as this, but in a much more compact form? And that's the ticket for us to get rid of the y equals x on that side, because we can do the same thing on the other side, and then we can simplify the equation and only have one side to remain and say, and still have y equals x, and then the other side does not need a term anymore. But the full derivation is going to be a lot longer than what it seems here.
So you'd say z equals x and y is greater than x. So you'd say z equals x and y is greater than x.
Z equals x.
And y is greater than x.
Well, because when z equals x, it also means, okay, z equals x, this is saying that x is greater than or equal to y. So this can also be broken up into this part here. And that's why it will cover the second term as well, because when when x equals y, then z equals x equals y, and it will be covered by the first term already. We just have to separate the equal to from the greater than or equal to so that we can, simplify the way it looks without changing its meaning. Okay. Any questions about this? Now, but you can see that if I wanted to, I can actually do this part step by step, and I can tell you exactly why one step can lead to the next step. How do we call this process? It's a mathematical. Is it a trace? No. How do you call this? It's a proof, exactly. It's a step-by-step proof, okay? Now, why don't I just say something like this? Okay, this is really actually important in terms of concepts, because when most people look at this statement here and look at this statement here, intuitively, some people can say, "Oh, it's quite obvious." They actually say the same thing, and I'm sure most of you or some of you will look at these two expressions and you say they really mean the same thing. Things are just arranged differently. So why can't I, or why should I not, just say it is obvious that this equation or this expression here is the same as the other expression? The same thing why we have to go through this proof here. Why do I have to go through this proof to show that this expression is really equivalent to this expression, even though to some people it may be obvious? Why do I want to prove it step by step or use a truth table and go through all these details, a lot of chores, just to get, to establish one step follows another step? Why is that necessary? Any answers? No? Yep.
If you don't do it, you're going to have a lot of mistakes down the line.
Potentially, yes. Okay, like I just made a mistake, right? And you spotted the mistake, I can go back and fix it, find out what's wrong with it. Okay, so at this point, I'll just kind of take this out of the context of this class here, and just give you an example of why it is important not to just say it is obvious this is the same as that. Okay, this goes all the way back to my graduate school days, okay, which was a long time ago. And when I was writing my dissertation, my professor, my advisor, told me, "Hey, Tack, you can just use this theorem, which is just a statement saying something is true. You can use this theorem as the basis of my dissertation and use that, and I can build on top of that." Okay. I looked at the theorem on the first time, and I thought, yeah, that seems to make sense. Okay, it's okay, I can use it. After a while, I started to have questions about it. I was thinking to myself, well, it seems to be right, but I am not quite sure. Okay, I just have this gut feeling that it may not be true all the time. And I told my professor about my gut feeling, and I asked, can I see the proof of this theorem before I start to use it in my own dissertation? A dissertation is just basically a long paper that you have to write before you get your PhD. So my professor said, well, sure, this theorem was proved in the thesis, which is a shorter piece of paper, a shorter paper when someone wants to get a master's degree. It's proved in the other paper. Just go over there and take a look. So sure enough, I dug up that master's thesis and tried to look for the proof. There was no proof. Okay, guess what language it used to lead to the theorem? Obviously. Obviously, da 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 da. Okay, so I was thinking, there's no actual mathematical proof that is step by step that I can follow. And then I started to have even more questions. So 1 week, I just said, I told myself, okay, I just cannot go on with my own work until I know the theorem is proven, because otherwise the foundation of my own my dissertation is going to be shaky, right? So I spent a whole week to try to find one counter example to prove the theorem wrong, and I did. I went back to my own advisor, and I showed him the counter example, and his expression was just, oh, that was it. Okay, not a very strong reaction. I went back to the AI artificial intelligence lab to meet with the other students, the other graduate student there, and I showed him the counter example. His master's thesis was entirely based on the theorem that I just proved wrong. And he just went ballistic. Because it really just negated pretty much the entire work that he had done for the past 2 years. Because he was using that theorem that was using the obvious proof technique. So that's why it is important for us to do these things step by step. May not be in this class. Okay, this class is not really the best place to do it. But when in your math classes, when you move on to cisp300, which is discrete structures, you will have to do your proof step by step. And it is important to be rigorous, because otherwise, sometimes you can skip a step, and something that is not true, and if you assume it is true, then really bad things can happen when you're writing programs. Are there any questions about the reason why we have to be kind of rigorous when we try to prove things, line by line, step by step? Any questions? How many people? Sorry?
Did you publish that?
Well, it's my dissertation, so it's all in the public domain. Yep. Because it's a UC, so it's funded by taxpayers' money, and therefore it belongs to the taxpayer. Whether it's useful or not is another, a different question. So there we have it. All right, so getting back to our example here. Now, our entire example last time was, let me see, where was the algorithm? Oh, okay. The entire thing was basically saying, okay, if I give you this algorithm, can I prove that Z is the maximum after line 5? That was the question. Assuming that I finish this proof here, in other words, I finish this derivation so that this expression will be equivalent to this expression, then I would have established that the algorithm is correct. Under what conditions? Do I need to make assumptions about x and y?
No.
Nope. It will work for all cases. So that means I don't even need to perform a single trace to know that my algorithm is going to work correctly. That's what we are doing here with the whole concept of pre and post conditions. Are we doing okay so far in terms of understanding why we are doing mathematical proofs instead of just tracing an algorithm, assuming certain values in variables? Is that part okay? The rationale part? The details is really misleading, and it can be distracting sometimes, but it's the rationale that is important. Are we doing okay? All right. But there are also other things that we can do with pre and post conditions. Sometimes I can give you a post condition, and I can ask you what is the precondition matching that post condition. I'll give you an example. Here's line 15. Line 15 says x gets x plus 2. And then I tell you what post line 15 is, okay? So the post condition of line 15 is x is, let's see, x is greater than, okay, let's make it more complex, okay? Let's make it 2x is greater than y, okay? that is quite awful, isn't it? Because I'm not telling you what x exactly is. I'm not telling you what y exactly is. I'm just saying that after line 15, I know that 2 times x at that time is greater than y. Twice the value of x is greater than y. I don't know exactly what x is. I don't know exactly what y is. But here's the question that makes it even worse. I want you to tell me what is the precondition of this. In other words, do I have to give up everything and say, I don't know anything about x or y before line 15 executes? Or do you think that I can still say something about x and y before line 15? That's the question. Okay? What do you guys think? Yep.
I'm thinking to disprove that 2x is greater than y, x can be a negative number.
X can be any number, it can be fractions. Okay, so let's assume x is a real number. So you can have fractions. Can we still say something about x and y or how they relate before line 15 in this case? Okay, we'll put this on the shelf right now, okay, and then we'll go with a much simpler example first. So let's say this is, okay, I'm going to move this out of the screen, scroll it out of the screen so that we don't have to deal with it. Okay, so here's another line which is 57. Line 57 is a simple line, y gets y plus 1. And instead of giving you something difficult like the other one, I'm just telling you that the post condition of line 57 is y has a value of 23 exactly. Can we, in this case, say something about the precondition of line 57? In other words, can I somehow undo what line 57 did to y and then make a statement about what y was before line 57 executed? It seems reasonable, right? Because what does line 57 do to y? It increments it by 1, okay? And after the increment, it became 23. So before the increment, it has to be exactly. Does that make sense? We are walking backwards. We're not executing a program in a forward fashion. We're trying to execute a program backwards. But does that make sense so far? When we have concrete values and the expression is relatively simple, we don't have any problem understanding it. But why am I doing this? Why do we have to execute programs backwards? Finding bugs, exactly. What are bugs? Defects, right? Errors, things that your program is not supposed to do. Do you think an error happens at do you think the symptom shows at exactly the same point where the mistake is?
Not necessarily.
Not necessarily. Very good. Okay. How about most of the time?
Almost never.
No, almost never. That's a very true statement. In other words, when you make a mistake in a program, it may not have any observable symptoms. The program continues to execute. Something is wrong. The variables may have the wrong value. You're on the wrong branch already. But nothing shows up until it prints the wrong message. The program crashes. It, for some reason, there's some observable output that says, okay, this program is no longer working correctly. But how far are you from where the mistake actually was?
Depends on how long the program is.
Potentially very
Depends on the complexity of the program, and it depends a lot on the program itself, the algorithm. So, can someone explain why we sometimes have to walk backwards? We start with where the symptom is, because that's the first place, and say, okay, we really should not be here, or by the time we are here, the values are all wrong. How do we get here? You have to go backwards. Okay? What were the values before we got here? You have to walk backward. So this is a debugging technique. Would that be useful? Remember the toothbrush? Your first job as a developer? This is going to be useful. Okay? Being able to think in this fashion and go execute a program backwards is going to be useful. All right, so we'll take a look at this statement. Yep.
So the pre-57 was given to us, right? Or we found it out?
No, we are only given post 57 in this case, and we just kind of, in this case, we use our gut feeling to find out what pre 57 is.
Okay, so, oh yeah, so 23 minus 1 is 22.
Yep, exactly.
Okay.
Okay, so here is another question. If I tell you, okay, I'm going to change this a little bit here, and I'm going to say, let's generalize this a little bit. This is line N, okay? And on line N, I have an assignment where x is getting f of x. Is everybody familiar with this notation, a function? Function f applied to a variable x. Kind of? No?
Yeah. Wow.
Yeah.
Okay, been a while. Okay. A function f in this case is really just some sort of operation that we apply, that we use x for that operation, for that expression, and it gives us a new value. And I'm using that value to put it back into x. Is that okay? I mean, am I doing okay so far with the concept of a function? Okay? And I'm not even saying whether it's an onto function, one-to-one, or anything like that. You know, we're just saying that it's some sort of expression. In other words, if I want to give you an example, you know, in certain cases, you know, f of x can be just x plus 1. I'm using the value of x, I'm just adding 1 to it. Or in some other cases, it can be x times 3, okay? In any case, f of x is really just an expression that has x itself, and it gives me a value. I'm using the value of x to calculate something. And then that's my right-hand side of the assignment, and I want to use that value to update x itself. Are we still doing okay so far? All right. So in this case, if I tell you that the post condition of line N is x equals k, okay? Can I do something about the precondition? Maybe. It depends on one important factor. The important factor that I'm depending on is, can I undo f? How many people are familiar with this notation? Well, this is actually f to the power of -1 of x.
Inverse.
An inverse function, exactly. How many people still remember the concept of an inverse function? I can go over that, it's not a problem. Okay, so we'll just kind of quickly go over the concept of an inverse function because it plays a very important role in this sort of thing. Okay, so we'll go ahead and kind of ignore this, roll this off the screen, and then focus on what is a function and what is an inverse function. We'll start with something like this. Okay, that's my function. In other words, if you tell me what x is, I'm going to give you back 1 more than what you gave me. The question is, can I find an inverse function? And in this class, I just use f prime to denote an inverse function because I don't have, you know, to the power of. So f of x is going to be x minus 1, right? The inverse function is basically undo. Okay, if you think about the word processor or spreadsheet, in the inverse function is undo. How do I undo something to get back the original thing? Are we still doing okay? Just in general? Okay. Now, how can I prove that f prime in this case is the proper inverse function so it can undo the original function? What about this? What if I apply f of prime to f of x?
You'll get x.
What should I get back? In other words, I'm applying some change to x, and then I decide, oh, let's undo that. What should I get?
Yes.
I should get back x, right? Okay. Should get x back. Okay. Well, let's see if that's the case. Can I prove it?
Yes.
Okay. Let's go ahead. Okay. What is f of x again? I'm just going step by step here. So first, I'm just using the definition of f of x here, f of x is just x plus 1, right? In other words, can I establish that equality?
Yes.
It's just replacement, right? I'm just replacing f of x by its definition. Are we doing okay? But what does it mean when I apply f prime on something? I'm just subtracting 1 from that something, right? So in this case, applying f prime to x plus 1 is really saying x plus 1, which is whatever is inside the parentheses, and then the whole thing minus 1. Can I establish that equality, the second line? Because that's the definition of f prime. I'm just taking 1 away. I'm taking 1 away from whatever you gave me. Are we still doing okay? And which rule in algebra should I use to go for the next step? Something that we used earlier. The associative law, which means we can change the parentheses. We can change the order of applying these operators. Well, technically I have to change this negative minus to plus first, but we'll just go ahead and change that. And what do we get back? It's just x. So are we doing okay so far with the concept of a function versus the inverse function? I can do something to a value, and then I can undo whatever I did to the variable. Now, not all functions have an inverse. In other words, there are some functions that can only go one way sometimes. It doesn't go the other way. I can give you one example. If f of x is, let's say, 0 times x, okay? What is the inverse function of that?
X times 0.
Nope, it does not exist.
F divided by 0.
It's division by 0, or it just does not exist. Now, why is that? I mean, why doesn't this exist? Now, this is not a math class.
0 is 0.
Exactly. It has to do with the fact that everything times 0 is 0. So given the result of function f here, I don't know where I start. Because I could, x could be 1, it ends up with 0. X can be 2, it ends up with 0. X can be anything, it ends up as 0. So if you just give me the end result of 0, I cannot reverse the operation and tell you what x was before the operation. Is that making any sense? So in this case, I don't have an inverse function to reverse it back to a single value. Other things can give you multiple results. If f of x equals to x squared, okay, this is squared. What is the inverse function of that? Plus or minus, very good. So that means, technically speaking, there are two values that can be used here, because this can be plus the square root of, this can be plus x. It can also be negative x. So in this case, it splits the path into 2. Now, if this is actually in your algorithm, you only know the result of the square. Now you have to say, okay, before this step, x can be this value, or it can be this value, because both can lead to the same outcome, the same result. Are we still doing okay so far with the concept of function versus inverse function? Okay. All right. All right. So what we'll do is we'll go back, oops, not that far, to here. And then we say, this is one case. Okay, is that making any sense? Okay. I can also do something a little bit differently. I can also say, if I know what is the precondition of line n, and let's say x equals a value k, can I say something about a postcondition here? Yeah? What can I say about the post condition? This one is easy. Just f of k. Okay. Are we doing okay so far? So now we'll go through, we'll actually work with one example here using what we have learned so far. So here's line 79. Line 79 says, x gets x divided by 2. And the precondition of line 79 says the following. It says, x is greater than y, and x plus 3 is less than z. That's my precondition. I want to know what is the post condition. So instead of going through the process, but this is a little bit different. Okay, this is a little bit different compared to. There are two ways to approach this. One way to approach this is to say in post line 79, we just replace everything else with f applied to it. Division by 2 applied to it. Because I just divide x itself by 2, so do you think this will work? Y divided by 2. Does that work?
Yeah.
Because I just divided the value of x by 2. So if I compare the value of x to y divided by 2, the relationship of greater than should still hold. Is that making any sense? What about the other side? The other side is a little messier because x is not on one side by itself. There's a plus 3. So that means on this side we have to kind of change it a little bit first, moving the 3 onto the other side, and then we can apply the function, which is in this case division by 2. Is that making any sense? But that's a lot of algebra work. Yep.
Wait, so those statements have to be true?
Yes.
Because if x equals negative 3 and y equals negative 4, y divided by 2 would be negative 2, which would be greater than those.
Say again?
If x equals negative 3 and y equals negative 4, negative 3 is greater than negative 4, but if you divide it by 2, it's negative 2.
But the second line is post 79, which means at that point x would have half the value of what it used to be.
Okay.
Yep. So yeah, that's the important part. Is we are taking a snapshot of the variable at a particular time. So this is right after line 79 executes.
Okay.
Yep.
So we're not trying to say if it's true or false. We're just stating what everything is post line 79.
We are saying it has to be true. What we are saying here is if you tell me this has to be true before line 79 executes, I'm telling you that this has to be true after line 79 executes. Is that okay?
Okay.
That's the whole idea of pre and post condition is if you tell me this precondition has to be true, I can tell you what is the post condition that also has to be true. Okay? But sometimes this approach is not very workable because what if this x here is deep inside some kind of expression and it's hard to isolate x on one side and have everything else on the other side? That makes it a little difficult, isn't it? So instead what we'll do is we can also do something about x itself because we can just say x times 2 is greater than y, right? Do these two statements mean the same thing? X is greater than y divided by 2 as opposed to 2 times x is greater than y. Are they saying exactly the same thing? They are? Okay. What about the other side? Instead of moving the plus 3 onto the other side, once again, I see x, I replace it with x times 2, plus 3 is less than z. Is that okay? In other words, is this comparison saying the same thing as this comparison? They are. Hey, so it looks like we have some way to, in general, deal with this kind of assignment statements. where the right-hand side is an expression that involves the same variable as on the left-hand side. And it's a reversible type of operation. Yep.
Why do you use multiplication on the third line instead of doing division with it?
Because, I don't, okay. First of all, let's take a look at line 79. What does line 79 do to x?
Divided by
It divides it by 2.
Right.
Okay? So that means after line 72, if I multiply the value of x after line 79, what do I get back? The value of x before line 79.
Okay.
So if I already know that it was greater than y before line 79, then I can also say that after line 79, if I multiply the value of x by 2, I get back the original value, and that is greater than y.
Okay.
And for the same reason, if I know that x plus 3 is less than z before line 79, after line 79, if I multiply the value of x by 2, I get back the original value of x, and that value plus 3 would still be less than z. Okay? We're basically undoing what line 79 did to x, and then so that we can retain the same expression or the same relationship between x and all the other variables and constants. Yep.
If at any point during this pre and post proof thing for your entire code that you could simplify any of that, you would immediately, right?
Yes.
Okay.
You would simplify, but without losing any information.
Right, right.
Yep. Mhm.
So you're saying that the pre is given, all you have to do is plug in the inverse function for the new variable.
Exactly. So once again, the concept of inverse function pops up again. Very good. All right. So let's see, how we can do this again, but this time using a much more formal method. Okay. So we'll scroll this off the screen so we can start from scratch again. So what I would do in this case is I will say use f of x to represent the right-hand side of line 79, the assignment statement. Okay. So in this case, what is f of x? It's the right-hand side of the assignment statement. It's just x divided by 2. In other words, I'm using f of x just as a notation, so that we don't refer to just x divided by 2. I just say it's f of x. Is that okay so far? I'm just giving it a name. I'm giving the right-hand side of the assignment statement a name. It's f of x. The next question is important, okay? Does f of x, or does f have an inverse? That's the question. Because depending on the answer, I will go one way or the other way. In this case, the answer is yes. The inverse function of f, in this case, I will use f prime to denote it, is what? It's just 2x. Okay, I can just write 2x here. Very good. Then what I'll do is I'll do the following. I'll use this template, and you will see this over and over again, and you have to use the same thing in your homework assignment. I'm going to use this template here. Post 79 is the result of some kind of substitution operation. When we use substitution, it means we search through a particular pattern, a particular original thing, we locate a particular pattern, and then we replace it with something else. Are we doing okay so far with the concept of substitution? We look through something, we look for a particular pattern, and then we replace that with something else. So in this case, what we are doing is we are looking through the precondition of line 79. We look for x, which is the left-hand side of the assignment statement, and we will replace it by f prime, which is the inverse function applied to x. And you will see this over and over again. So I'm going to comment here and say what that means. So I'm going to use a pound sign to say this is just comments. It's the common notation for most scripting languages. So this means we want to look, search through pre-79, locate all instances or occurrences, whatever you want to call that, of x, and replace each occurrence with f prime of x. That's what we are doing with the sub operator. Are we doing okay so far with this? Do you know how to do this in a word processor?
Find and replace.
Find and replace, exactly. That's what we are doing, but to a particular expression and not the entire text. Okay. So the next step we want to do is to expand what is pre-79. Do we know what is pre-79? Yeah, we do. This is our pre-79. So we'll just go ahead and copy that to expand what is pre-79. Do we know what is f prime of x? Yeah, we do. It's just 2x. Now, I would put parentheses around it, just so that it doesn't change the meaning after the substitution. The next step is really just to carry out the substitution. In other words, what I'm doing here is I'm taking this expression and I'm just saying, do we have any occurrences of x here?
Yes.
Yeah, we do. Okay, here's 1. What do we replace it with?
2x.
2x. And I'll put it in parentheses, just so that it works in all cases. And here's my next occurrence. We replace it with 2x in parentheses. I'm done. So this is a fairly straightforward and mechanical way to deal with assignment statements like line 79. The most difficult part of this is to ask the question, or to answer the question, does the right-hand side seen as a function of the assignment statement, does it have an inverse function? That's the most difficult part, is to find the inverse function. Are we doing okay so far with this? Does it work though? Is it working the way it's supposed to? Let's apply this to something that's really simple so that we get a good feel that it is actually working fine. So we'll scroll this off the screen and we'll work with something that's really simple. We'll work with line 31. Line 31 says y gets y plus 1. We'll start with a precondition of line 31. And in this case, I'll make y equal to 44. Okay? We'll apply the same technique. Okay? I know most of you will say, oh, I know the answer already. Post 31 is y equals 45. I know you know the answer already, but I want to use this technique to see whether it works. Okay? Because that's the whole purpose of doing it here, is to see whether it works or not. So we'll go through the entire motion just like last time. So in this case, we'll use f of y to represent the right-hand side of line 31. And in this case, it's just x, y plus 1. Is that okay? I'm just giving the right-hand side a name so that I can say the inverse function of that. Does f have an inverse? Does it?
Yes.
Okay, what is it? What is f prime?
Y minus 1.
Y minus 1. Okay, so y minus 1. All right. So we're going to apply the technique here. We'll look up the template. So what is the template? The template says post 31 is the result of a substitution operation. What am I searching through? The precondition of the same line. What am I looking for? The left-hand side of the assignment, which is y. What am I replacing y with?
Y minus 1.
The inverse function of y. The inverse function of f applied to y. Next, I'm just going to expand out some of these things. What is pre-31?
Y equals 44.
Y equals 44. And what is f prime of y? Y minus 1. Can I do this substitution mechanically? Okay. So to do this mechanically, I start with the original expression, and then I ask myself, do we have any y's in it?
Yes.
We got 1. What do we replace it with? Y minus 1. I'm done. Is that giving you a reasonable result? Is that right? Because y minus 1 equals 44. If you simplify that one more time, it becomes y equals 45. So it does work. Okay. Any questions about what we are talking about here? No questions? Okay, but what about those tricky cases when there are no inverse functions? Let's take a look at those cases. So we roll this off the screen, and then we'll use another example. So we'll use line 89 as an example. Line 89 says x gets a constant value of 5. Okay. So in this case, we'll go ahead and go through exactly the same thing, except we'll follow a different branch at a certain point. So in this case, we'll just do the same thing, and we'll name the right-hand side f of x. In this case, is the right-hand side of line 89, and it's 5. It's perfectly okay to have f of x to be a constant. There's nothing wrong with it. Even though it does not depend on x, the expression does not depend on x, it can still be a function of x. It just maps every single value of x to 5. It's still a function, but it's a function that has no inverse. So the next question that we ask, does f have an inverse? The answer this time will be no. It is not reversible. If it's not reversible, what are we going to do? If it's not reversible, this is what we'll do. We'll say post 89. I'm going to talk about the template first before I even give you the precondition. Okay, because the most important part is how do we apply the mechanism like this without having to think about it. We'll say that it's a forget operation in this case. Okay? In other words, what we are doing is we're forgetting in pre-89 anything that mentions x. And we will state x equals 5 after this, because we know that x has a value of 5 after this entire thing. So if I want to comment on this, I would say forget pre-89 x means remove all components in pre-89 that makes use of x. Okay? We're trying to forget items or forget components that says something about x before line 89. Let's go ahead and make this a little bit more complicated. So let's just say that I also tell you what is the precondition of line 89, and it can be fairly complex. We can say x is greater than y, and y is less than or equal to 2z, and x does not equal to 20. Okay, that's fairly random in general. So now let's go ahead and see if we can apply this rule here. So in the next step here, I'm going to expand what is pre-89. Fortunately for me, I can copy and paste. That's why I don't want you guys to spend too much time copying, because you guys will have to actually copy everything. If you remind me to upload this, it will be uploaded. And I'm hoping the recorder is still going.
We need to read the roll.
Sorry?
Roll call. Have you done the roll call? Yeah.
Oh, roll call. That's right. Forgot about that. There you go. We have about 20 minutes. I think that's more than enough time to put your initial next to your name. All right. So that's our pre-89, the precondition of line 89. We're going to forget all the components that will mention x, and then we'll say x equals 5. So now you have to look at this entire thing here, and then you say, does this have anything to do with x?
Yes.
Yeah, it does. So we have to get rid of it. How about this one here? It doesn't mention anything about x. We can keep it. How about this one here?
Yes.
Yep. Okay, so what we'll do is we'll only keep that one. But we also have to remember one more thing, because we do know that x equals 5 at this point. That's the forget operation. The different branch, or the only different thing about this has to do with f does not have an inverse in this case. So instead of using a substitution operation, we have to forget something that we knew before, because that would not hold true anymore. Are we doing okay so far with this? Yep.
X still does not equal 20 though. So why is that one being removed?
Well, because
contextually it's still true.
Contextually it's still true, but x equals 5 is more specific than x does not equal to 20. In this case, it's only this because you can do that only because x has a very specific value after this operation.
If you reverse them, if you took x equals 5 as part of the precondition and made the line, the assignment x does not equal 20, then it would not have the same argument.
But not in general. I understand what you're saying. What he's saying is a very interesting point is, what if x equals 5 before, right? But you're already thinking about a trace and not as a pre and post condition. Okay, what you're saying is, because what you're saying is you're already adding one more thing to the precondition, because what you're attaching to the precondition is x equals 5. And that's not what is given here. X can be 5 in this case, but it may not be 5.
What I'm saying here is if the line condition, line 89, was x gets the value, or x becomes x is not equal to 20, and the precondition is x equals 5, the forget would make x not equal 5 anymore, but would not be equal to 20. That's, both conditions are still technically true at that point, but you would still have to forget x equals 5 because x does not equal 20. That
Okay,
doesn't
hold
make
on,
any
hold on.
sense.
Okay, you're changing the line 89 to something else, right?
Yes.
You're changing line 89 to,
X does not equal 20.
but you cannot do it. There's no such assignment statement. Okay, I think I know what you mean. What you are saying is you want to make, okay, tell me how you want to change line 89. So I'm going to say 89A here as an alternative. Okay, x gets what?
X does not equal 20. X.
Aha, okay, x does not equal to 20. Okay, this is entirely different from x gets 5 or something like that. Okay, let's take a look at this statement here. This is not a bad statement, it just means something that is entirely different from what we are used to. Okay. Okay, this is the not equal operator, okay? When we have x does not equal to 20, what is the outcome of this? Is it an integer? Is it a value, numerical value, or is it a true-false value?
True.
It's a true-false value. X is either, okay, the outcome of this is either true, x does not equal to 20, or false, x does equal to 20 in this case. But it's not a numerical value anymore. Am I?
I don't see where the problem is in that specific section there. Yes, that is true, but what does that matter in the rest of the context of this section here?
Maybe that doesn't matter, but you're following rules, so that way if something comes up that does matter, it still follows under the same rule.
Well,
Maybe
then
an
becomes,
exception
okay,
or something.
because you're changing the type of x too. Okay, what does x have to be in order to compare that to 20?
X has to be a number.
A number,
If X is
exactly.
okay.
So
now I get it.
x changed its type from a number to a Boolean, and that changed the meaning of the original assignment statement entirely. Yep. I think I understand what you're saying is, you have an assignment statement where you're assigning anything other than 20 as the value. right?
All I was trying to say is that if you have a statement that is more precise than a statement that you're giving, then you would still be forgetting the older, less precise statement.
You'll be losing precision. You'll be losing
But the
information.
forget would still make you be losing.
Correct.
You would still be forgetting the older assignment, even though it was more precise, which was your argument for why you were forgetting the less precise statement is because it was less precise.
Correct.
But you would be forgetting a more precise statement if you were giving a less precise
Correct.
one.
Because the actual way to do this is not just to forget. I know what you're saying, yeah, but I think the class maybe is getting a little confused.
Sorry.
So for it's okay, for this class we'll just use the forget operation, but what you said is actually correct. We only want to lose any type of detail that conflicts, that can potentially conflict with the new detail. That is absolutely correct. But in this class, figuring out that part, is can be a little bit difficult already. So that's why I'm making it simplified and just forget things that we already knew about the variable that is changing. Is that okay? Yeah. Okay. All right. So let's go through an example with a few steps and see if we can apply these rules that we just learned. So here's a new program. We'll start with line 1. Line 1 says x gets 5. Line 2 says y gets x plus 1. So right off the bat, we have some little tricks that we have to apply here. And then line 3 says y gets a new value, which is 3. And we want to find out what is the post condition of line 3. Okay? You think we can do it? All right. Well, we can trace this. This is easy to trace because we do have specific values. But I want to do the proof and not the trace because I want to illustrate how to apply everything that we learned earlier today. And we'll start with the precondition. Line 1 does not have any particular statement. It just says pre1 is true. What does that mean again? What does it mean when I say the precondition of a line is just true? What am I saying about the values of the variables? Absolutely nothing. So this is my way of saying I don't know anything about the variables because the true is the simplest expression that is true. Okay. And what are we going to do about this? What is post 1? Well, in order to know what is post 1, we have to go through those questions again. So we'll go ahead and say f of x is 5 on line 1. F has no inverse. Apply the forget rule. So that means the post condition of line 1 is us forgetting in pre1 whatever that mentions x, we have to forget it. But we also have to say that x equals 5 after line 1. Okay. The next step is to just factor in what is pre1. Pre1 is just true. Does true mention anything about x? No. Okay, so we can keep that. So it becomes true and x equals 5. Can we do something about this kind of awkward looking expression? Do you still remember what is true relative to conjunction? It's just like 1 times whatever is whatever. So true is the identity of conjunction. So we can now simplify that to just x equals 5. Are we doing okay so far with this step? I know it seems really long and unnecessary to know that x equals 5 after the assignment statement, but remember, we are trying to illustrate the process of using these rules. Yep.
Yeah, so post 1, forget pre1, and then how do you say it further with x? For post 1, we have to forget the pre1, right?
We are looking through pre1, and then we have to forget all the components that mention x. But since pre1 is just a statement, an expression true, it does not mention anything about x, so we get to keep the entire expression, which is just true.
Okay.
And then we simplify true and whatever to whatever, because true is the identity of conjunction. What can we do about pre-to? Because if we want to figure out what is post-to, we first have to know what is pre-to. What can we do here? Right? Does that make sense? Because those two statements are sequential. One is following the other one. About post-to, how can we figure out what is post-to? We ask the same questions, right? So in this case, we say post f of y is x plus 1. Do you think it is reversible? Is there an inverse? Are you sure there's an inverse? Because x and y are independent variables. It is not reversible. Okay? So in this case, f also has no inverse. Okay. Well, if it has no inverse, we know we have to apply the forget rule again. So now we have to say post-to is to forget certain things in pre-to, potentially forgetting something. Anything that mentions what? Anything that mentions y, because y is the one getting changed and not x. All right, this is the important part, because otherwise we can be forgetting things that we should not be forgetting. What else can we say after after line 2?
Y equals x plus 1.
Okay, y equals x plus 1 for sure, because that's the effect of the assignment statement. So now we just have to look at this and say, what is pre-to? Well, pre-to is just knowing that x equals 5. Does x equals 5 mention anything about y? No. So we can keep it, because we only want to forget components that has any mentioning of y. So we can keep x equals 5, the whole thing. And on top of that, we can say y equals x plus 1. Now this is where it gets a little bit tricky, because you want to take this one step further and say y equals 5 plus 1. In other words, when you have an equality here as a part of a conjunction, you want to apply that equality and replace as many occurrences of a variable as possible with just the constant. Okay? In other words, you want to reduce the reliance on the mentioning of other variables. Yep?
But isn't y is mentioning on the bottom x equals 5 and y equals x plus 1?
But that's outside of the parentheses. The forget operation is only this part.
Okay.
The conjunction is outside of the forget operation. Okay? And now we can try to deal with post 3. Okay. So in order to figure out what is post 3, we have to know what is pre 3 first. So pre 3 is post 2, because these two statements are sequential. And then we have to apply the same thing here. We say f of y, in this case, is a constant 3. F has no inverse. There's no way to reverse it. So once again, we apply the forget operation. And that means the post condition of line 3 is the forget operation applied to the precondition of line 3. And this time, what are we forgetting? Let me extend the screen a little bit so we can see. That's line 3. We are forgetting everything that mentions y. Okay. And after line 3, what can we say? What do we know about y? Y equals 3. Very good. And then we can just go ahead and apply this whole thing. What is pre 3? Well, pre 3 is this mess here. We just stick it here. I'm doing this step by step. In other words, the second step is really just substituting pre 3 with the actual pre 3, and then we will go ahead and apply the forget operation here. Look through this entire thing, which is our precondition of line 3. Is there any component here that mentions y?
Yes.
It's this component, right? So we have to get rid of it. So after we get rid of that component, we have x equals 5 and y equals 3, and that's our post 3 in this case. That seems to be a lot of work when we could have just traced it. Right? What is the difference? In terms of the approach, yes, go ahead.
This is an absolute.
This is universal. In other words, I do not have to start with any specific values in this case. Yep.
Maybe I missed some point. For the posterior, why don't we do the algebra, which is 5 plus 1?
Because it's not reversible. Because f of y is x plus 1.
Yes.
That's not reversible because it maps, or it regardless of what the value of y was, the new value only depends on x.
Oh, okay, I see.
That's why. So it's not reversible. In general, if the function does not mention the variable in parentheses at all, it is not reversible. I shouldn't say in general, in all cases. Are we doing okay with this approach? Okay. Let's see, we have about 4 minutes left. What I want to do in 4 minutes is not to go through another example or any new rules. I just want to point out where in the notes you can find this stuff here. This is 3.1. It talks about constant assignment. If you scroll all the way to the bottom, there's a lot of explanation here which you should read too. At the bottom here, you will see the forget operation, and it gives you an example of the forget operation. So we have covered this stuff already. And then the next one is assignment statements that refer to itself. So in this case, if you scroll all the way to the bottom of this screen here, you will see the stuff that we just mentioned here, the substitution of the precondition, and we take the variable that is on the left-hand side and we substitute it with the inverse function of the right-hand side. So it's the same stuff that we have talked about, just presented a little bit differently. And that's where we are currently at this point. So what we want to do is you guys have to read up, section 3.5 before Thursday. This is the stuff that we talked about already, how a path splits into two, and how we can figure out the precondition of each branch, and how the two post conditions have to merge to the post condition of the entire thing. So we talked about this already, and if you go all the way to the bottom, you will recognize something that we are fairly familiar with already. The V symbol here is really the OR operator. Okay? Now for the brave ones, you can go to loops here. Because loops are quite different compared to assignment statements and conditional statements, because guess what? It goes back to a certain point. Okay? So the reasoning of try to derive the pre and post conditions for a loop can be, guess what? Loopy. It's a little bit loopy because you have a precondition that can potentially have a component of its own post condition because it goes all the way back. So that's what we'll talk about on Thursday. So if you read ahead of me, you will probably get a head start, and you can absorb it a little bit better on Thursday. I'll see you guys on Thursday.